Hello everyone, I hope you are all doing well. I am Tamer Hassan Fahim. I am going now to present our research paper entitled Age of Information Optimization using a Hybrid Preemptive Non-Preemptive Discipline, co-authored with Professor Sharif Rabia, Professor Ahmed Abdel Malik, and Professor Wahid Zahra. The outline of our presentation is divided as follows. An introduction to real-time status update systems, the motivation and the corresponding objectives, the proposed system description, the performance analysis of our work, the obtained numerical results, and finally, the conclusion and our future work. So first, let's give a brief introduction to real-time status update systems. Recently, smart IoT systems have been widely deployed in real-life applications, such as smart manufacturing systems, healthcare monitoring systems, and infection contact tracing systems. All these systems have a common communication paradigm, that is, real-time status update systems. To demonstrate its structure, let's consider an example of temperature monitoring system, where the ambient temperature is detected by a temperature sensor, the temperature signal is discretized by a sampler, all samples are converted into status update packets containing the sampled information and the timestamp of information. All status update packets are transmitted through the network to the interested recipient. The received packets are processed by a server in order to be converted into readable information for monitoring and control purposes. In such systems, receiving outdated packets leads to inaccurate monitoring and control decisions, which degrades the system reliability. Accordingly, information freshness is a critical quality of service requirement for such systems. It is well established that maximizing information throughput or minimizing information delay don't imply enhancing information freshness. Accordingly, a new metric called the age of information has been recently coined to quantify information freshness. Age of information is a monitor-related measure, which reflects to what extent the information at the monitor is outdated with respect to the information at the transmitter. And it can be mathematically formulated as T minus G of T, where G of T is the generation time of the latest packet received at the monitor. To demonstrate its evolution, let's consider two status update packets generated at time G1 and G2. After receiving the first packet, age of information increases linearly with time. Upon receiving the second packet, age of information resets to some lower value before increasing one more time. So let's now present our motivations and the corresponding objectives. First, we found the deployment of buffer-free systems demonstrate higher significance in mitigating information backlogging, and thereby enhancing information freshness and efficiently utilizing network resources. Accordingly, we make further enhancements in the age of information performance for buffer-free systems. Second, we found a primary deployment of classical service disciplines, preemption and non-preemption, throughout the age of information literature, where the fresh arrival request can be admitted or declined. The preemption discipline under buffer-free systems achieves the age of information optimality for single-source systems, conditioned on exponential service time distributions. However, there are two main drawbacks for such disciplines: non-guarantee of optimality under a general service time distribution, and the inadaptability to variations in network and traffic conditions. Accordingly, we aim to redeploy discretionary preemptive disciplines, or so-called hybrid preemptive non-preemptive disciplines, that were previously initiated in the priority queuing system context. In such disciplines, the preemption can be admitted or declined based on a specified discretionary rule. Finally, we found a very limited study of the hybrid preemptive non-preemptive discipline in the age of information literature, specifically probabilistic hybrid discipline and interruption frequency-based hybrid discipline. Accordingly, we aim to propose a new hybrid discipline based on different discretionary rule, that is, elapsed time-based hybrid discipline. To conclude, our main contribution is that we add to the literature of the single-source system by proposing an elapsed time-based hybrid discipline through buffer-free systems. So let's now present our proposed system description. We consider a buffer-free single-source system modeled as M Erlang 1.1 queuing system with +1 arrival process, Erlang service time distribution with the shape parameter k and the scale parameter 1 over mu. The Erlang service model can be decomposed into a sequence of k exponentially distributed service phases, and it has the following motivating features. Modeling real-life applications such as multi-hop networks, approximating other service time distributions that are analytically involved or experimentally obtained, quantifying the elapsed service time in terms of the operating service phase tau. The dynamics of the proposed elapsed time-based hybrid discipline can be demonstrated as follows. For any fresh arrival request to a busy server, we firstly monitor the operating service phase tau. The preemption can be only admitted if the operating service phase doesn't exceed a predetermined threshold T. Through the extreme cases of the threshold parameter T, we can obtain the full preemption and the non-preemption disciplines. For our performance analysis, we evaluate average age of information under a general setting of the threshold parameter T. We deploy the stochastic hybrid system approach, which is most commonly used for finite state systems, memoryless servers, and when the system descriptor is a hybrid of discrete and continuous components. The first step is to define the system descriptor, which is a hybrid of discrete state representing system occupancy and the continuous state representing age of information tracking process. In our case, we have a one-dimensional discrete state space to track the server availability and the operating service phase tau, and the two-dimensional age of information tracking process to track the age of information signals through the server and the monitor. The discrete state dynamics can be modeled as one-dimensional continuous time Markov chain, whereas the continuous state dynamics can be modeled in two different cases. At the holding case, where there is no discrete state transitions, age of information increases linearly with time. At the transition case, age of information signals resets to some lower value. This resetting is linear and can be mathematically formulated as matrix transformation equation. We construct a stochastic hybrid system transition table containing all possible discrete state transitions and the corresponding age of information resetting. For the discrete state transitions, we have the following stochastic events: arrival to empty server, arrival to busy server, where the server service preemption can be admitted under a specified condition, inner departure between service phases, outer departure to the monitor. For the age of information resetting, we have the following cases: fresh arrival entry to the server, where the signal x1 reset to 0, departure to the monitor event, where the signal x0 reset to the value reached by x1. Otherwise, there is no change in the age of information process. We evaluate stationary state probabilities by solving a system of linear equation constructed by the global balancing equation and the normalization equation. We evaluate the correlation vector VQ, which contains the average values of the signal x0 and x1 at each discrete state Q. Using this formulation, we can solve a system of linear equation to find the VQ. Finally, we can obtain the average age of information at the monitor using this formulation. For our numerical results, in the first numerical study, we validate the analytical framework by establishing a simulation environment similar to the proposed system description using MATLAB. The simulation time is large enough to ensure steady-state results. As we can see, the analytical and the simulation results are closely matched with higher precision values. In the second numerical study, we conduct an optimization problem to minimize the average age of information, where the threshold parameter T is the corresponding decision variable. We compare this problem with a similar problem for the probabilistic hybrid discipline, where the preemption probability parameter is the corresponding decision variable. Both problems are solved using excessive search method to find the optimal solution. The optimization results are further compared with the full preemption and the non-preemption disciplines. under two different settings of the Erlang service models. As we can see, the preemption discipline is no longer the optimal under Erlang service model, in contrast with the case of exponential service time distribution. However, our proposed model fulfills the age of information optimality through the two Erlang settings of the Erlang model and under all different loading conditions. It further demonstrates considerable performance gain for time-critical applications. Moreover, the performance gain particularly increases under highly dispersed Erlang service models. In addition, by investigating the optimal threshold parameter T, we found that the proposed discipline is efficiently adaptable to variation in traffic loading conditions. To illustrate, upon increasing the offered load, the optimal threshold parameter decreases to reduce the preemption possibility and thereby enhancing information freshness. However, it should be noted that at the heavy loading conditions, the optimal threshold parameters converge to 1, allowing the preemption only during the first service phase. This is mainly due to the memoryless property associated with the operating service phase, the first operating service phase. For our conclusion and the future work, the age differential performance of buffer-free single-source systems have been addressed. The classical disciplines pose a dilemma of inadaptability and non-guarantee optimality. We propose an elapsed time-based hybrid discipline through an Erlang service model. A controlling parameter T is introduced for the proposed discipline. The average age of information is analyzed using stochastic hybrid system approach. The proposed disciplines fulfill the age of information optimality with a considerable gain. The performance gain is significant under highly dispersed Erlang service model. The proposed model is efficiently adaptable to variations in traffic loading conditions. For our future work, we expect extensions to general service time distributions. In this regard, we suggest extending the stochastic hybrid system analysis of the Erlang model to the case of phase type distributions, motivated by a previous stochastic hybrid system study of hyper-exponential service time distribution. We also expect extensions to the case of multiple sources with priority, motivated by our previous work in this regard. This paper is based upon work supported by Science, Technology and Innovation Funding Authority SDF of Egypt under grant number 48186. Professor Sharif Rabia is a project PI. Thank you, everyone.